Hey everyone! Have you ever tried to learn how to code but got stuck? In my new Python programming class, we're going to break that loop. This course is primarily focused on people who are complete beginners, so don't worry if you don't have any background. This course is different than other courses because we're going to teach you to think like a programmer and solve problems like a robot. So let's get started. So in the last video, we talked about translating between numbers and letters and how this is going to be useful for us. So that was we had a three-step process: translate letters to numbers, perform some operation, and go back to letters. And this is how we're going to create our cipher. The main thing we're going to focus on in this video is to perform some operation. Now, if we go back to the very, very beginning, we can remember this, and I'm going to copy this and paste this down here for us so we'll have easy access to it. We remember that we're translating between particular letters to other letters, and this is based on a left shift of 3 using Caesar's cipher. And what we did was we go back a certain number of letters. So here we go back 3 letters. You go A, Z, Y, X, and then we have A is associated with X. And then this cipher is just this written out. So X, and then B, A, Z, Y. So we just move everything over 3 values. And this was our idea. Now, to generalize this, we're going to want to be able to move it over any number of values to create a cipher. And that was the motivation for us doing this in this particular way. Rather than just being able to do this one particular type of cipher, we want to be able to use any number of shifts because that makes it easier for us. If everyone always knew that we were going to use the left shift 3 cipher, the one that Caesar actually used, then it wouldn't be much of a secret message because everybody would know it. So there's 26 possibilities now that we can use in each direction, really. So that's quite a bit more useful than just being able to do this one particular cipher. So the way that we can do this is actually using Modulo. And if we go back to the original page that we were looking at on Caesar's cipher, it actually gives us this formula here. Encryption can be represented using modular arithmetic by transforming the letters to numbers according to this scheme, and then encryption of a letter by shift n can be described mathematically as this formula. And we're going to shamelessly just use this information. We're not going to really think about how to solve this, and we'll talk a little bit about why this works in a second. But for now, we're just going to copy this over. So we have, this is the encryption. We take x plus some shift mod 26, and then x minus some shift mod 26. And remember, in the real world, you can always do this. There's no need for you to reinvent the wheel. This is already something that has been figured out for all of us. So we're going to remember it, I'm going to write this down as we're going to define 2 functions to determine the new number, right? So the encrypt number, it takes in a number. And what we're going to do is we're going to add another value, argument to this called shift. This is going to be something else we're going to provide this function. And the shift, we're going to default it to 3 because that's what we've been using. Now, actually, the shift is in terms of a right shift. So that right shift, it says this up here. So this is a right shift of 23, right? Okay, so let's use that. So what we're going to do is we're going to say, okay, addition equals number plus shift. So this is, I'm going to keep switching back and forth. This is number plus shift. This modulo part is what we're going to handle next. So we're going to say return addition modulo 26. So that percentage sign will do modulo for us, and we could do this modulo 26 and just perform exactly what it says in the Wikipedia article. Now, if we look at decrypt number, we're going to take in a number, do shift. And it's the same idea, but instead of adding the shift, we're going to subtract the shift. So we're going to say subtraction equals number minus shift, and then return subtraction percent 26. And then this is going to do the calculation for us. Okay, so why does this work? That's another question. That's the second part of the question. And I would recommend in general to look at things from both sides, right? You want to be able to solve the problem yourself, but you also want to be able to use information that's out there on the internet. In this case, this is publicly available information, so you could always look something like this up, and there's no shame in using those kinds of formulas. Again, no need to recreate the wheel. So while this gives us a solution, it's important also to understand it. Because I think if you understand how this works, you'll be able to use it in a lot more use cases than just looking up a formula. While I said we could just shamelessly look up the formula, let's talk a little bit about why this works. So modulo, we talked about in an earlier video, but I didn't go too far into it. Modulo is like a clock. That's the way that I would think of it. Clock in the sense that it goes back on itself. So a clock is modulo 12. There's no 13 o'clock. It goes back 1 once it goes through the whole cycle of 12. And that's the same idea with a modulo. A modulo will only vary when you do something modulo something else. You're only going to get returned a value between 0 and that number. Or 0 and that number minus 1. In this case, we're only going to get a number between 0 and 25, which is exactly what we want. If you think about it just purely logically, if we have some function, we need to make sure that whatever it returns out of here is only going to be between 0 and 25. Using modulo will ensure that happens, right? So it ensures that we're not going to get like 26, which we wouldn't know how to translate. And what this really amounts to is what I mentioned before, is like looping back on itself, right? So in this case, let's say we're at Z, right? And we're doing this shift 3, which would be going ahead 3 values, because this is a right shift, right? So in this case, it would be going up 3 values. But if you just use this and you try to go up, there is no letters after Z. So that'd be a problem. You get an error, right? Same idea of what we actually did here, right? If we try to go up from Z, it's not going to work because there's no letter after Z. So basically, modulo lets us just loop back around, right? It's going to go loop back around and go to A, B, C. Mathematically, the way of representing this is using modulo. Is this idea of looping back around is really the idea of a modulo. So thinking again of a clock also loops back around in a way. So this is one way of understanding modulo. The other way of understanding modulo is what I mentioned last time, is in terms of remainders. So it's the remainder from a particular value. Like a clock, 13 o'clock is really just a remainder of 1 from 12, right? If you divide 13 by 12, you get 1 remainder 1. And the modulo is the remainder itself. So that's another way to think about modulo. In general, modulos are going to be useful for things that are like a loop, like a cycle, and numbers can only be between certain values. So in this case, what we're going to do, to give an example, for encryption number, so let's say we take A, right? A was 0, and we're going to say A plus 3. So we're going to go to A, so that would be 0 plus 3, which would be 3. And then what we're going to do is we're going to take that number and do it modulo 26. Because 3 is less than 26 and greater than 0, or greater than or equal to 0, nothing happens. We just use 3. So in this case, we just moved A up to 3, and then 0 up to 3. So A goes to 0, then 0 goes to 3, and then 3 would return D, right, if we translate it back. So now we're just translating A to D. Now, if we were looking at Z, on the other hand, this is where the modulo becomes important. Z was translated to 25, right? 25, we would add 3, so we get 28. Now, 28 is outside or greater than 25, right? So we're going to want to, that's what the modulo 26 is going to come in handy. So what we do is 28 divided by 26. That would give us 1 remainder 2. Okay, so that 2 is actually what we're going to get back out of the modulo operation. So 25 plus 3 is 28. Modulo 26 is going to be 2, if we do that just all in our heads. And that would return C in this case, which is, again, the same idea. Z, A, B, C. We go up 3, right? So this is the same idea. This is what we were talking about with Caesar's cipher of shifting numbers, right? Letters. Now we're going to formalize it using modulo. We can have this. So there's a couple of ways to think about it, and whichever way makes the most sense to you is the one that you should go with. One thing that I like to think of a lot is, what can I possibly have in here? And then working backward from there, right? I know that whatever this is going to come out of this can't be outside of 0 to 25, right? Because I don't have anything that's going to work in that way, right? I haven't associated a number to 26. So interestingly, if we want to think about what happens, there actually is an error, a particular error in Python if you try to find a key in a dictionary that doesn't exist. So to illustrate that, just so it's clear why we need to make sure that the number is there, if we try to look up 28, which we just discussed would be Z plus 3 or 25 plus 3, this will come up with a key error, which is a particular type of error, which, as I mentioned before, there are key value pairs in the dictionary. And if it can't find the key, in this case 28, it couldn't find this 28 in this dictionary because it's not there, then it's going to return a key error. That's another way to think about it, right? We can't have this key error. The only way to ensure that doesn't happen is to make sure that there are numbers only less than or equal to 25 and greater than 0. So no other numbers can really exist in here. Okay, so let's talk a little bit about how this all worked. Let's do this with a particular letter, right? So first of all, that 3 shift, as I mentioned, this is a right shift. So to make this obvious to us, let's put in right shift here. And we're going to change every value that has shift. If you don't do this, it's going to complain because it won't know what shift is inside of that function, right? So now we have this right shift, and then we're going to say it's equal to 3. Actually, what we've been doing, and I'm going to change this default argument again, is making it 23. Now, a default argument here, I skipped over this a little bit. A default argument is an argument that we pass into a function. Arguments are things that we're going to have as inputs. So number is one input, and right shift is another input. Now, a default argument means that we don't have to specify that argument. That means I don't have to say what right shift is. And if I don't, it defaults to 23. So the default argument is just what it's going to do if you don't say anything. But you can change it if you want. So let's run this, and let's actually do this for a number. So encrypt number. Let's do it with 25 because we've just been talking about this. And it's going to do a right shift of 23. So this returns 22. Now, what does that mean? Let's talk it through. It's going to be 25 plus 23, which is going to be 48. Then we're going to do 48 modulo 26. So 48 modulo 26 is really the remainder of the division of 48 and 26, right? So 48 divided by 26 is 1, remainder 22, right? The remainder is 22, and so we get 22. That's the number we get. Seen in another way, we're going to go from Z, and we're going to go up 23 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, which was equivalent to our left shift of 3. Remember, 1, 2, 3. So that was what our original algorithm was saying, was to go from Z to W. So this is what we were originally looking at. Now that's using the default argument of right shift 3. If I change this to right shift 1, we're going to end up with 0. Which again would be the result of that operation. Z would then be going just directly to a right shift of 1. So this is the general idea, right? So this is, first off, a couple of things we've learned here. We learned about default arguments to functions, meaning that we can pass in an argument to a function that has a value that's already set. And if we don't put anything in, if I just put in this one argument, it's only going to plug in number. So it says number is equal to 25. Right shift, because you didn't put it in, is 23. But if I do put something in, like 1, it's going to say number is equal to 25, right shift is equal to 1, and then calculate everything for us. So that's one thing. The second thing that we talked about was this idea of the encryption and decryption based on, first off, the Wikipedia article, and then we talked through how Modulo works and how this would make sense. Okay, so now we have this operation. This is the operation we want to perform on that number. So we got the second part of the equation finished. Next video, we're going to put everything together. We're going to translate letters to numbers, perform the operation, and then go back from numbers to letters. Once we're there, we have successfully done our encryption and decryption algorithm, which will be great. And then we're just going to formalize a couple of things there and talk a little bit about next steps and how we would go about cracking this algorithm.